The fundamental theorem of calculus is a bridge between integration and differentiation. Differentiation is a local process. By differentiation, we compute slopes of lines tangent to the graph of a given function at given points. The only thing that matters in such computations is what the function does near that particular point. Integration, on the other hand, is global. We define the definite integral as a limit of Riemann sums, and in this definition, what the function does on the whole interval from a to b comes into play. These integrals are very useful. They can be used to compute areas of domains, volumes of solids, lengths of curves, and so forth. They have also many other practical applications. Therefore, it is highly desirable to be able to compute precisely definite integrals. And the fundamental theorem of calculus, or rather the second part of that, gives us a tool to do just that. It says that if capital Case f is an antiderivative of the function small case f, then the integral from a to b of the function small case f x dx equals capital Case f evaluated at b minus capital Case f evaluated at a. Very useful result. Let us start by recalling the basic properties of integrals. The first property tells us that the integral from a to a, f of x dx, is always zero regardless what function f is. That is, the integral over an interval whose length is zero is always zero. The second property tells us that the integral of a sum is sum of integrals. The third property tells us that the integral of a function multiplied by a number is that number times the integral of the original function. The fourth property tells us that integral from a to b f of x dx is a negative of integral from b to a f of x dx. And the fifth property is additive property. It tells us that the integral from a to b of f of x dx equals integral from a to c plus integral from c to b of the same function. If c is between a and b, this seems completely obvious on basis of the definition of the definite integral, and if c is not between a and b, the same result is still true, but then we need to use the property form to prove it. In these considerations, we assume that all the functions are continuous, without making a separate note of that. As a preparation for the main result, observe that if the functions g, f, and h satisfy g of x is at most f of x is at most h of x for all x between a and b included, then the integral of g of x dx over the interval from a to b is at most the integral of the function f, and that is at most the integral of the function h. If these functions are non-negative, then these integrals correspond to areas of domains. And the double inequality is completely obvious because the domain under the graph of g is fully contained in the domain under the graph of f, and that is, on the other hand, fully contained in the domain under the graph of h. But this double inequality is valid regardless whether these functions are positive or negative. It suffices that they are defined and continuous. A corollary of this is that if capital Case M is the maximum value of the function f on the interval from a to b, and small case m is the minimum value, then the integral from a to b f of x dx is bounded from the above by the integral of this constant capital Case M over the interval from a to b, and that integral can easily be computed. It is b minus a times capital case M. And it is bounded from below by b minus a times small case m. And this again is also completely clear on basis of this diagram. If the function f takes positive values, then the domain under the graph of the function f fully contains the rectangle with base AB and height m, and is fully contained in the rectangle with base AB and height capital case M. And therefore we have this double inequality. We use the previous considerations to justify the following. For a continuous function f, we may find a point c between a and b such that the integral from a to b f of x dx equals f at c times b minus a. If f takes positive values, then the integral from a to b f of x dx is the area of the domain under the graph of f and over the interval from a to b. And this statement simply claims that we can find a point c such that the area of the rectangle shown here in this picture is the same as the area of the domain under the graph of f. Let us take a little closer look to this situation. So here we have the graph of the function f, and the domain under the graph of the function f is bounded by x-axis and the vertical lines x equals a and x equals b. We claim that we may find a point c such that the area of the rectangle drawn here with the red top and the base interval from a to b is the same as the area under the graph of this function. So when we draw this rectangle, we leave something out and we take a little bit too much area. What we take too much is this blue domain. It has two parts, note. Also on the left there's a little part that belongs to the blue domain that is not contained in the domain under the graph of the function f, but we also leave something out. So we have to choose c so that the area of the yellow domain is the same as the combined area of the blue domains. And that is indeed possible. We assume that the function f is continuous on a closed interval from a to b, and we claim that there is a point c between a and b such that the integral from a to b f of x dx equals the function f evaluated at c times b minus a. This is called the mean value theorem for integrals. The proof is based on the previous considerations. Since the function is assumed to be continuous on a closed interval, it does attain its maximum value capital case M at some point of that interval, and it also does attain its minimum value small case m at some point of that interval. And by the previous considerations, we now know that b minus a times small case m is at most the integral from a to b f of x dx, and this is at most b minus a times capital case M. Now b is larger than a, so b minus a is positive, and we may divide this double inequality by b minus a. When we do that, we divide all terms of this double inequality by b minus a, and b minus a cancels out from the left and from the right. And therefore we have that small case m is at most 1 divided by b minus a times integral from a to b f of x dx, and this is at most capital case M. Now the function f was assumed to be continuous. It attains the value small case m, which is its minimum value. It also attains the value capital case M, which is its maximum value on the interval from a to b. And a continuous function attains any value between any two of its values. Now this number 1 divided by b minus a times integral from a to b f of x dx is between the two values of the function f, small case m, and capital case M. And therefore, by the intermediate value theorem for continuous functions, we know that there is a point C between a and b such that 1 divided by b minus a times integral from a to b f of x dx equals f at c. By multiplying by b minus a, we get that the integral from a to b f of x dx equals f at c times b minus a. So we found the point C satisfying this equation. Therefore, the proof is complete, and we have the mean value theorem for integrals. In the fundamental theorem of calculus, we assume that the function to be considered is continuous. The fundamental theorem of calculus has two parts. The first part, or the first fundamental theorem of calculus, says that if f is a continuous function and if we define the function capital case f by setting capital case f at x is integral from a to x f of t dt, then the function capital case f is differentiable, and the derivative of the function capital case f is the function small case f evaluated at x. An example of the use of this is the following. Let capital case f be the integral from 0 to x e to the negative t squared dt. We cannot express this function in terms of elementary functions, so this is a special function. It's an important special function that has many applications, especially in statistics. Now our task is to compute the derivative of this function capital case f. And the solution is to observe that the function e to the negative t squared is a continuous function. It is continuous everywhere. Therefore, we may apply the fundamental theorem of calculus, and we may conclude that the derivative of the function capital case f at x equals e to the negative x squared. So there is no computation involved. We may write down the expression for the derivative immediately by simply taking the function to be integrated, in this case e to the negative t squared, and by replacing t by x. Then we get the derivative of this integral from 0 to x e to the negative t squared dt. Next, we prove the first part of the fundamental theorem of calculus, the first fundamental theorem of calculus. We claim that if the function small case f is continuous, then the function capital case f, which is defined as the integral from a to x f of t dt, is an antiderivative of the function small case f. To this end, we have to show that the derivative of the function capital case f at x is the function small case f at x. So we compute the derivative. Let h be different from 0, and we consider the change f at x plus h minus f at x. This is the numerator in the expression whose limit is then the derivative as h goes to 0. So this f at x plus h minus f at x is, by definition of the function capital case f, integral from a to x plus h times f of t dt minus integral from a to x f of t dt. But these two integrals can be combined by the properties of integrals to one single integral. It is the integral from x to x plus h f of t dt. The picture here on the right illustrates this situation. The integral from a to x of f of t dt is the area of the blue domain. The integral from a to x plus h of f of t dt is the area of the blue and red domain together. So the difference of these two integrals is then the area of the red domain, which is integral from x to x plus h f of t dt. In this picture, h is positive, but the same result is also true if h is negative. So now, by the intermediate value theorem for integrals, just discussed a moment ago. We know that there is a number ch between x and x plus h, such that capital case F at x plus h minus capital case F at x, which is the integral from x to x plus h f of t dt, is the function small case f evaluated at ch times h. Then next we divide by h. H is not 0. So we get from that equation that capital case f at x plus h minus capital case f at x divided by h is the function small case f evaluated at c at h. But the derivative of the function capital case f is the limit of the left-hand side of this equation as h goes to 0. And the number ch is between x and x plus h. This means that as h goes to 0, ch will approach x. And this means that since f is continuous, f at ch approaches f at x as h approaches 0. So we conclude that the derivative of the function integral from a to x f of t dt, which is a limit as h goes to 0 of the quantity capital case f at x plus h minus capital case f at x divided by h, is the same as the limit as h goes to 0 of the function small case f evaluated at c of h. And then since c of h approaches x as h goes to 0, this limit is small case f at x. This proves the first part of the fundamental theorem of calculus. The second part of the fundamental theorem of calculus, the second fundamental theorem, states that if capital case G is any antiderivative of a continuous function small case f, then the integral from a to b f of x dx is g at b minus g at a. So this is a statement. If capital case G prime equals small case f, and if the function small case f is continuous, then integral from a to b f of x dx is g at b minus g at a. So to prove this, observe first that by the first part of the fundamental theorem of calculus, the function capital case f, which is defined by setting capital case f at x to be integral from a to x f of t dt, is an antiderivative of this function f. Furthermore, the integral from a to b f of t dt is capital case f evaluated at b. So we have to prove that the integral from a to b f of x dx is g at b minus g at a. And to that end, we consider this function capital case f, which is a special antiderivative of the function small case f. By the definition, capital case f at a is 0, and capital case f at b is the integral from a to b f of t dt, as already observed. This means that the integral from a to b f of t dt is capital case f at b minus capital case f at a, because capital case f at a is 0. So this particular function capital case f satisfies this statement of the second fundamental theorem of calculus, the second part of the fundamental theorem of calculus. We must show that also this arbitrary antiderivative capital case G satisfies the same equation. So if G is any antiderivative of f, then there is a constant capital case C such that capital case G equals capital case f plus this constant function C. This is by the mean value theorem. Therefore, capital case G at b minus capital case G at a is same as f at b plus c minus f at a plus c. C cancels out. We conclude that g at b minus g at a is f at b minus f at a. And this means that g at b minus g at a is the integral from a to b f of x dx, proving the second fundamental theorem of calculus, or rather the second part of the fundamental theorem of calculus. The previously shown two parts of the fundamental theorem of calculus together form the fundamental theorem. The first part states that if small case f is a continuous function, then the function capital case f defined by setting capital case f at x is integral from a to x f of t dt is an antiderivative of the function small case f. And conversely, if capital case g is any antiderivative of the function small case f, then the integral from a to b f of x dx is capital case g at b minus capital case g at a. This is a very useful result. We use the following notation. The integral from a to b f of x dx, which is now capital case g at b minus capital case g at a, is substitution to the function capital case g at x from a to b. And we use two different notations depending on the situation to this fact. We may write simply bar and then subscript and superscript a and b after capital case G, or we may include capital case Gx within square brackets and then use the subscript a and superscript b to indicate the substitution from a to b. So the notation capital case Gx bar ab or capital case Gx in square brackets ab is read substitution to g from a to b. Let us take an example. Compute the integral from 0 to pi sine of x dx. This is the area of a domain bounded by the graph of the sine function over the interval from 0 to pi. We know that negative cosine is an antiderivative of sine. Therefore, the integral from 0 to pi sine of x dx is a substitution to negative cosine of x from 0 to pi. When we substitute the upper limit, we get from negative cosine pi, we get 1. And from the lower limit, we get negative cosine at 0, that is negative 1. So the substitution is 1 minus negative 1, and this amounts to 2. So we conclude that the integral from 0 to pi sine of x dx is 2. James Gregory, a Scottish mathematician, was born in 1638 and who passed away at the age of 38 only in 1675, found the first proof of a restricted version of the fundamental theorem of calculus. Now you may wonder how this is possible because Riemann sums were invented only about 200 years later. Clearly, Gregory must have used a more primitive version of the concept of the integral. But he is credited for finding the first proof of a restricted version of the fundamental theorem. The first proof of the full version was found by Isaac Barrow, an English mathematician. He was born in 1630 and passed away in 1677. He also lived only 47 years. He discovered the fundamental theorem of calculus, and he was the teacher of Isaac Newton. Isaac Newton was born in 1643, passed away in 1727. He was the founder of differential and integral calculus together with the German mathematician Gottfried Leibniz. Leibniz was born in 1646, passed away in 1716. He was the co-founder of differential and integral calculus, and he is the person responsible for the notation df dx for the derivative of the function f. So df dx is written as a quotient, but is not a quotient, it's a notation for the derivative. These four great mathematicians have created what we have learned today.